Also working?
And can you hear?
Hello? Hello, good morning. I think now is working. Let's start.
Yeah. But I'm not sure you can how to say hear the voice of online attendance. But yeah.
No,
Anyway.
Yeah, now we are online. But there is some problem. How to do full
Oh, so sorry.
slide? This is okay?
Yeah. Okay.
It's working. Okay. Thank you very much. Good morning. So okay, thank you very much for having me here. Good morning, everybody. Today, I'm going to discuss in my presentation the gauge dependence issue on of waves during radiation and matter domination eras. This is the motivation of my talk. Gravitational waves begin after detection of gravitational waves by LIGO and universe gravitational wave probe are new physics beyond the standard model. Tensor perturbation induced by scalar perturbation or scalar induced gravitational waves are useful tool to study the physics of the early universe. The tensor perturbation at first order are gauge invariant, still at the second order tensor perturbation may be gauge dependent. Issue of the production of scalar induced gravitational waves investigate in each gauge. The modest goal is to show the evolution of the energy density in diverse gauge. In particular, the induced gravitational waves are used to constrain on PBA scenario, and conversely, the PBA constraint, primordial black hole constraint, can be recast as the constraints on the induced gravitational waves. So this is the agenda of my talk. So this is the agenda of my presentation, the source of the cosmological gravitational wave, background, importance of diverse gauges, computation of results and vision and future directions. So here, first of all, I will discuss the cosmological sources of gravitational waves. First of all, I talk about the fluctuations. Basically, these are the primordial tensor perturbation, tensor fluctuations. Due to these tensor fluctuations, gravitational waves are generated by primordial scalar fluctuations in the second order of perturbation. So it is true that the induced second order gravitational waves is expressed by the square of the curvature perturbation, but it can be sizable and can even become larger than the primordial gravitational waves if the primordial curvature perturbation are enhanced at this small scale compared to the CMB scale. Apart from the induced secondary second order gravitational waves, other mechanisms of gravitational waves are one of them associate with preheating, phase transition, cosmic strain, and additional sources are SUV gauge field and Eigen field. So actually, for future study, I'm highly interested to use these sources to discuss the induced gravitational waves. Here is a short explanation that induced gravitational waves are also called the second order gravitational waves or secondary gravitational waves. Further, you can see in this reference. So let's talk about, yes, please.
If you are interested in this, where primary compensation and small scale, scan for the interpretation by primary black holes.
Accompanying black hole. So basically, this is very hot topic. So we can accompany with primordial black hole, and further, in addition, right after the detection of the direct detection of the gravitational waves, most recently by the pulsar timing array data, we can also further discuss by observational data these theoretical studies of the gravitational waves. Before, basically, until now, basically, who are discussing these studies theoretical point of view. Now further we can discuss by using pulsar timing array data, to observe studies. We can further discuss a complete black hole. So a little bit talk about the background about the gravitational wave, secondary gravitational wave. Here this is basically linear perturbation around Minkowski space-time. Here we have just wave equation around Minkowski. Similarly, we can further discuss around FRW perturbation, and we have this kind of equation. Further, for this equation of motion, we have the following solutions. These gravitational waves basically called the primordial waves. These are invariant and too weak to be yet observationally. Almost until now, it's impossible yet to detect them. Here, I just have to show just how to wave produce from the video. Okay. Further about scalar induced gravitational waves in Poisson gauge. Basically, the main agenda is scalar gauge dependent scalar induced gravitational waves in different. So the typically chosen gauges are Newtonian gauge. So basically, in the literature, have already discussed almost gauge. We have to discuss in other gauges these scalar induced gravitation. So first talk about the gravitational wave gauge. So here are some, by using this perturb metric, so have this kind. So here Hij, tensor perturbation shows gravitational wave, and psi and scalar perturbation. So here we use this psychedelic graviton action, and further there are to gravitational density. This we can find in these references. So here are some basic equations, some basic formulas to address the power spectrum of energy density. Here we use Fourier components or Fourier transformation to find the dimensionless quantities. So here one of them, it's a power spectrum. We can find power spectrum. Further, and we find the fractional energy density of gravitational waves using this formula. Further study, the detail can be found in these references. Yeah. It's something.
Outside.
It's
No, I don't know.
it will issue some.
What about we try?
Issue some.
Yeah. Just you can explain to the online speaker.
Yeah, because I don't think I can make that.
Okay, so we have to change the room.
Yes.
So should
No.
bring,
Oh, I guess just
just bring my laptop.
just
Okay.
this here.
Oh, I see. Yes, so disconnected for a while.
I will bring your knowledge.
It's okay, no problem.
Oh, okay.
Yeah, we can maybe further come bring this stuff. We have to go. Which room? Don't have it. No,
No.
not this one. You please bring that.
No, you can just continue. I will use computer and we can continue talk.
Okay. So further, we have to discuss gravitation in Poisson gauge, and here, this is scalar-reduced gravitational waves in Poisson gauge. So here we have the equation of motion for the tensor mode source space scalar perturbations. So you can see here, H and is equal to AH, and the source term of the scalar perturbation is given below. So here are some basic formulas. Further, you can see where P is equal to this is the equation of state, and this is a scale factor. And here we use the green function to find the solution of this equation of motion. So here I just want to I have a short explanation that in the second order equation, the squares of first order quantity also pair. The first order perturbation of the energy momentum tensor can be related to the derivative of the gravitational potential, where the first order Einstein equation. The time evolution of the source function, when we have to discuss the time evolution of the source function, we have to study, to find out the solution using this source term. So here, are further quantities. We just have to find out the solution for the scalar perturbation. This is the scalar perturbation. This is basically a gravitational potential that obey this equation. Here we have the boundary conditions using for this equation to find the solution of the gravitational potential. So further, the primordial values is related to the curvature perturbation as given in the following formula. So here are some, dimensionless parameters. Here, don't be confused with x, so that this is not a special coordinate. So that here, little talk about this short explanation that we define the primordial value of phi k as being well before the horizon entry, but not too early as so that the equation of state of the universe at the primordial time is the same as that at the horizon entry. So further, Poisson gauge also called Untitled further study can be found in these following references. Here, the function, kernel function in the Poisson gauge. So we have to find using the source term. We find the kernel function using this formula. Further here, f u v x is contains the source information in Poisson gauge. So in the following, this is the formula that contains the source information. Here, let's talk about the short explanation here. That note that the integral defined power spectrum includes the square of the single function, basically the kernel function. So this is actually kernel function and the source function are also symmetric under the exchange of the u and v components. So here, let's talk about the importance of the diverse gauges. Why we use different gauges? One of them, there are different gauges yield different physical interpretation, so that we have to study scalar-induced gravitational waves in different coordinate system or in different gauges. So understanding the secondary gravitational waves in various gauges is crucial in each gauge. This study basically enables comprehensive analysis of the early universe, so that it is also crucial to discuss almost in the popular gauges. Apart from the issue of the choice of the physical gauge and the true observable measured by gravitational wave detector, the gauge dependence requires us to calculate scalar-induced gravitational waves in each gauge. Last one, importance, but not least, is in particular in each gauge, we have to show whether the observable energy density provides a clear physical basis for the short wavelength limit quoted in this recent paper. We are using pulsar timing array data. So further, we are working on this problem recently to address further scalar-induced gravitational waves. So now let's talk about the results of scalar-induced gravitational waves during radiation domination. Here RD mean radiation domination. So forgive me that I didn't, write the detail. What I mean RD. RD mean radiation dominated era. So here talk about the formulation. It's almost a similar formulation, but here like we used before in Newtonian gauge. But here you can see in this equation, basically this equation is a equation of motion of scalar-induced gravitation waves. Here tau ij is a projection tensor. S is basically source term. So here you can see this source term is different from the previous one that we discussed in the Newtonian gauge or in the Poisson gauge. So that basically this source contains all the information for different gauge choices under the consideration. So this source, so that this is a very long expression in this expression. So here we used the coordinate transformation to find out the kernel function. Basically, the main goal to find the kernel function to address the energy density of scalar-induced gravitational waves. Here are some basic formulas. We use the coordinate transformation to find out this kernel function I chi. So here, since the time dependence of scalar-induced gravitational waves in the integral kernel, we explicitly calculate the analytical expression for the kernels in Poisson gauge, in synchronous gauge, in every gauge. Further, during radiation domination, the Poisson gauge to the other gauges, we have to discuss the energy density of scalar-induced gravitational waves are so that we have to find the solutions from a Newtonian gauge or Poisson gauge to other gauges. So that this is our further modest goal. So we can obtain the solution in any other gauges by replacing the kernel function using this transformation for the evaluation of energy density. So here during the radiation domination case, in synchronous gauge we have this this kind of formulation. Basically, this is the transformation of scalar perturbation we have to use for the scalar perturbation. So here we find using the equation of motion, this is the basically of solution. Here you can see there are some constant. These are the integration constant, but here these cause some residual gauges. We use a boundary condition to remove these residual gauges. Further, we have the kernel function, to find out the kernel function, we use this source function to evaluate the kernel function. So here, we find that this source function using the transfer function of the scalar perturbation, which related to the curvature perturbation. So here the question is arises that the main difference in different gauges lies basically in the kernel function. So once we get kernel function, then the energy density of the scalar induced gravitational waves can be calculated. So that we, this is the main importance to discuss the kernel function, to find out the kernel function. Here during, yes, please. This one? Yes. Yes, please.
Is this prime time derivative?
Yeah.
I see. I'm wondering why there is a first order and first order time derivative. Is it come from Einstein equation or something?
This come from, yes, Einstein equation. Yes, basically this is perturbed Einstein equation. Yeah, this is perturbed Einstein equation. We use perturbation in the Einstein equations. So we use perturbation in the equation of motion. So that then this come from that equation.
Okay, I wonder. This Einstein equation is second order equation.
Scalar?
Second order.
Second, yes, second order. It's a second order equation. Yes, basically, this is the second order equation. You can see here.
Yeah.
Yeah, this is the second order equation. Yeah. This is perturbation. I just drew the tensor part. Yeah, include with the scalar perturbation. Yeah, scalar perturbation. So that here we have just on the scalar part. Basically this E is our scalar perturbation. Okay, so that we have just a time derivative of this scalar part. Yeah. Basically, this is the temporal component of the special component we didn't use, so that we have just a time derivative of this equation. Yeah. Basically, in these scalar perturbation, we use late time evaluations, so that we are discussing this scalar perturbation. Scalar perturbation is component of the time derivative.
Okay.
Yeah, it's temporal part, not the spatial part. So that we have just this kind of equation.
Oh, so I see that. You mean, Einstein equation is second order.
Yeah.
And you put the how to say, if you put scalar potential to as a source,
Yeah, source term.
then you have first order.
Yes. Yeah. Yeah. This is that. This is that. Yeah. Yeah. Your idea. Thank you. Yeah. Further, in the uniform density gauge here, you can see we just find the previous calculations. We just have the final result because the lack of time. I didn't write all the details. We just have the result of kernel function in uniform density gauge. Here you can see this is basically growing terms, and here the factor 3 square root is a sound speed. And here you can see it is worth mentioning that the term is growing mode without oscillation, and the above expression. So it does not contribute to scalar induced gravitational waves. Beside, the divergence has appeared due to the growing term in the gauge, in this gauge, which causes the breakdown of the linear perturbation. You see, we need to address this problem and a presentation a gauge invariant framework where the discrepancy of the energy density of scalar induced gravitational waves upon the uniform density gauge is shown to be eliminated. So that here you can see in this gauge, basically we have a problem that in this gauge maybe it will break down the perturbation, linear perturbation. So that we have to find a solution where we can sort out this problem. So that was basically a motivation that how to further address this problem and extend this work. Here, for different gauges, I just present the result of the kernel function. You can see here, basically this is our paper, this figure taken from we presented a relation with different gauges and found different result which showed the gauge dependence of scalar induced gravitational waves. So without picking up the physical oscillator, the results are different in diverse gauges. So here you can see this is these results basically shows the gauge dependence. Maybe basically this is a different result. If it overlap or have same result, then we can say that this problem has a gauge independent. So we have to find this problem also. Basically, theoretical point of view, it is okay, but from the physical point of view, it is not okay. So we have to find a way to find that where these gauges have same result, almost same result, or coincide with each other or overlap like this graph. So next we have to address this problem. Yes, please.
I'm not sure why.
This is theoretically is okay. Theoretically, just we have to find. Theoretically is okay, but from physical point of view, it is not okay.
Why practical view is okay?
Sorry.
Why practical view is okay?
Yeah, you can see. Just theoretical point of view, we have this kind of result. Here we can see from this result that this is gauge dependence. Dependence means basically we have different results. Okay. Yeah. This is one thing. So from a physical point of view, the energy density should not depend on the background or on any coordinate system. Basically, this is a coordinate system. Different coordinate system. We want to talk about the gauge. So, physical point of view, this result should be same. This is the main point. So, from the theoretical point of view, we got the different result. So, here question arises. So, this is not a physical point of view. Okay. So, this is main question that from the physical point of view, this is not okay. So that we have to find a solution or find further way to discuss this problem to physical point of view. So this is theoretical point of view might be okay.
See.
Yeah.
Does it mean you calculated it?
Yes.
The calculated value is not observable.
Not observable. Not observable.
It's kind of energy density or something.
Yes. This is the energy density. Basically, this is the information of the energy density. Basically energy density depend on the kernel function. These are the kernel function. This is energy density information. But the problem is that energy density is a physical quantity. So it should not depend on any background or any gauge. So this is the main problem. So that we have to find this from the physical point of view. So that we are using perturbation. So we have to find another way. Another way is that where we have to tackle this problem to find the same result. First, we have to use some theoretical point of view. Then we have to prove it these results from a physical point of view. So from the theoretical point of view, we try to solve this problem so that here are some similarly we have matter domination case. In this matter domination case, we have the same result almost. Basically, theoretically, these are the different results. This is the different debate that matter domination result and theoretical results are different. So that you can see here the results are different from the previous one in the matter domination case. So here the question arises that why do we talk about this radiation phase and matter domination phase? So secondary waves produced during radiation and matter domination phase, but the quantum fluctuation during the inflation provides the sources for the scalar induced gravitational waves. Because the propagation of gravitational waves depends on the background, and the scalar perturbation are different in different phases. Different phases mean in radiation and matter domination phase. So we consider scalar induced gravitational waves in both radiation and matter domination phase. So because the above reason, the observation of the scalar induced gravity can use be the further thermal history to for our universe. So here is the summary for the matter domination case. You can see here also the results are different in various gauges, in different gauges. You can see basically these results are from theoretical point of view, and these needs to be further discussed. So that we try to solve this problem using a general matching approach here further to tackle this problem. Here you can see similarly we used the perturbation metric here, the first order scalar perturbation, basically psi and phi. PE are the first order perturbation, and the second order tensor perturbation, Hij. Here, this second order scalar reduced tensor perturbation have the wave equation, the following wave equation, and this tensor perturbation, you can see here we just introduce a term. Basically, that term is called, chi, KL. This term basically, are the counter term. So this term will, be used to solve this problem, or that cause the gauge dependence or cause the divergence in the previous studies. So that here we introduce this term. So this is using this term, the problem of the gauge dependence or the divergence in the previous studies will be sorted out. So that similarly we have the formulation for further to study the scalar induced gravitational waves. For the W here, using the equation of state for the radiation domination case and matter domination case. So further you can see the detail in these references, provided references. Similarly, yes, please. Yes, please.
You take another.
No. Now I just told that before that was a problem that in different gauges that the result was gauge dependent. Okay, so but we tried to solve that problem. There also in some gauges there was a divergence that break the linear perturbation. So that we try to solve that problem, that no, there should be a way that we have to find the gauge independent result, are the, basically it should be the same in every gauge, physical point of view. So that from proving that result, we introduce a counter term. All the, almost the calculation are same, but here in the tensor perturbation, we introduce a, a one term, basically chi KL. This term basically called the counter term. We name the counter term in the secondary tensor perturbation. So that further, let's see the previous result. So with using this counter term, so what will be the change in our previous results? So that this is the main agenda. Okay.
Defining
Yeah, Hij, here we introduce chi KL with the projection tensor. You can see here chi KL is equal to -2 into 4e partial phi and partial e. Here you can see this expression. Basically, this is this expression on scalar perturbation. You can see.
Oh, okay.
Yeah, these are this contains this expression contains the scalar perturbation. So that in the previous studies the perturbation the dependence was coming in the scalar perturbation. You see, so that here we use again the scalar perturbation part to sort out that problem. That caused the dependence or that caused the divergence in the previous studies. So that we have to use this perturbation to tackle this problem further. So here similarly we have the we first have to try to find a result in radiation domination case. here you can see this is the kernel function. This is the transformation of kernel function. The one last term is we just add one last term using the new perturbation that called the counter term. Here I chi is the another term, the new term in this study, so that we have to find the result in this TT gauge. So here you can see it is worth mentioning that the terms contain both oscillating and non-oscillating terms. The only oscillating term here contributes scalar-induced security. Extra terms may cause the discrepancy in the energy density. Here, when you talk about the oscillating term, so only sine x or cos x, cosine x term are, cosine term are the oscillating term, the rest of the terms are non-oscillating terms. You see? So that that may cause the divergence. So here the question arises that, so is there any way to find these fictitious terms? These basically called the fictitious terms that cause divergence or that cause dependence. So here in this function, kernel function, we just found that this result basically in TT gauge result. So it is, you can see almost as a coincide or similar with the previous Newtonian gauge result. So here we find the gauge independent kernel function. Though basically we try to fix this discrepancy by adding a counter term that remove the fictitious terms in the secondary perturbation. You see, so that this is the result after using the counter term. So that similarly we have to find using basically, as I said before, in this expression, you see, this is basically a gauge independent kernel function expression. So that we have to find in different gauges. So let's see, like we have to find in TT gauge. Similarly, we have to find in a uniform curvature gauge. So here we also see using that counter term here, we have the gauge independent kernel function. Similarly, we can find out the gauge independent kernel function in rest of the gauges. Here I just present the graphical comparison in different gauges. You see here, this is the graph basically like before I just presented. In this graph, you see without picking up the physical oscillating term, we find the gauge dependent in different gauges. So results are basically different for different values in different gauges. So this was the main issue that we have to sort out, so that we use that counter term. So that counter term we have used. Now you see, using that counter term, we found all the result of energy density are same in different gauges. You see, so that was the main issue that we have to solve. Basically, the main problem is that you see our equation basically the energy density, the main physical part. So that should not depend on any gauge. That was the main issue. Okay, so that we just found that this is the main part, so that we try to fix the discrepancy by adding the counter term that removes the fictitious term in secondary perturbations. So similarly, we have to find result in radiation in matter domination case. So result in different gauges, you see W is equal to 0. It means that is matter domination case. Here are some different results. You see here cos sine x, basically these are the oscillating terms, the rest are the non-oscillating terms. We see that the other terms are the non-oscillating terms. Here in different gauges, you see these non-oscillating terms are quite different from the previous study. So that here we also find the different gauges. In similar way, we can find other gauge results for other gauges. Here, just I want to talk about the physical point of view when you talk about the graphical interpretation. Here, similarly, you can see the results show different, in different gauges. That was a problem that result basically, first time we present the graphical comparison in this study, that even in you can see here are not it's kind of simple curve like some are straight curve. You can see basically these curve shows the different behavior in meta domination case. We have to sort out this problem for different gauges. But here we tried using that previous as I told the counter term, we have same result almost. That result overlap and for different gauges. So here also another case of the meta domination case. So here we use the constant factor. There was coming constant factor in each kernel function. If we remove, so we have this kind of expression, but still this expression is also different, for different gauges. So that was the main issue, that the energy density should not depend on any background, on any gauge. So that here we finally we found the solution of this problem in meta domination case. Here you see all the results overlapping. So that happened after using that counter term in now it shows that this study that our results are same in different gauges. Let's talk about the conclusion. We derived basically general formula that investigate secondary perturbation from Poisson gauge to other gauges. We have found that the gauge dependency appear only in the tensor perturbations coupling with scalar perturbation, not in gravitational waves. It is to be noted that each kernel function contains oscillating term and represent scalar gravitational waves, and the other do not contribute. We have found that the gauge independent function using a counter term in the tensor perturbation that remove the fictitious term. Resultantly, the energy density of scalar induced gravitational waves is the same in different gauges, and the scalar induced gravitational waves are gauge independent. Here, we tried to solve this problem partially, but it's not, you can see it might be discussed for further using the pulsar timing array data. We have to check further that from the observational, data, this is true. This is our further debate we are working on. So there are some future direction that we working on figuring, finding out that the gauge invariant tensor perturbation further. In particular, each gauge we have to show that whether observable energy density provides a clear physical basis, a short wavelength quoted in this recent paper. We have to explore further primordial black hole dark matter accompanied with scalar induced gravitational waves. We have to find. Okay, thank you very much.
Can I ask a question?
Yeah, please.
I want to ask future this
Yes, please.
you mentioned gauge case of population.
Yes,
It's not population, i.e. if there are some gauge independent population.
yes.
It's inconsistent variable.
Sorry.
Inconsistent variable is gauge independent.
What?
Inconsistent variable.
Yes.
Is gauge independent, but I'm sure.
Actually,
Anyway,
it might be.
I guess there are some gauge variant.
Those are gauge invariant. Yes, I think so. Yeah.
Population and
Yes.
you want to you want to find the counterpart of this population.
Sorry. Could you please?
there are no engaged by physical dimension
Yes.
of
Yeah.
until after our.
Yeah.
So you want to find out what is the case?
Yeah, gauge invariant. We have to find, further. In general, you can see particularly that these studies drew from the observational point of view, from the physical point of view, we try to find that is okay. But is it okay from the observational data point of view? If we use observational data that these studies are okay, or to find out, this is the main further our intention to study that we are working on. Yes.
Ask one question.
Yes, please.
Is there as an object aside of the this information, but which is gauging not gauging independent and say
You mean which meaning?
I want to say, can you apply this kind of method to another thing? So you in this one you concentrate on kind of this evaluation in the context of repetition.
Yes, we can apply this study on the primordial black hole study. If we talk about the primordial black hole, we can further. This is the main question that the previous studies only have been discussing on one gauge, Person gauge or Newtonian gauge. A company to study the primordial black hole. Basically, when we talk about the scalar perturbations, we discussed primordial black hole to enhance the scalar perturbation. To generate, to discuss the primordial black hole, so that further, is it possible that we maybe with this study that now our results are same like in Newtonian gauge, this is possible that we can further study primordial black hole in these different gauges also. It was not discussed, I think, so until now. So people have been discussed this in only one gauge, particular gauge, Newtonian gauge, and Poisson. But the rest of the six gauges did not, study from the physical, from the point of view of the primordial black hole study. So that maybe we can further check whether in those gauges, is it possible to generate, to produce a black hole? The production of a black hole might be possible to discuss in different gauges using this study. This is the application. It could be application. Yeah, yeah. This could. Yes.
And that's all question.
Okay. Thank you very much.
You.
So, oh, sorry. Speaker. 杨佳悦。杨佳悦在吗？
Hello，在。
哦，可以开始了。
好的。我共享不了，因为他人正在共享。请问声音清楚吗？能看到屏幕吗？请问能看到屏幕吗？Okay. Should I start now? Okay. Hello everyone. My name is Jiayue Yang. I'm a second-year master student from Roman and Liash's research group, and I'm from Yuvacharu and the Perimeter Institute. Today, I would like to talk about the dynamic behaviors of black hole phase transitions near quadruple points. And this presentation is based on this paper. First, I will give you an introduction on the black hole thermodynamics, and then we will talk about the quadruple points in black hole phase transitions. Next, we will study the dynamic processes at the quadruple points, and also the first passage events. Finally, I will make a conclusion. So first, what are black holes? In 1783, John Michell realized that the gravity of star could be strong enough so that the escape velocity of the star may be bigger than the speed of light. And he names the star the dark star. And this is the first motivation of the black hole. And then in 1915, Albert Einstein proposed the general theory of relativity. And the next year, Schwarzschild obtained an exact solution of the Einstein field equations. And so now we have the exact definition of the black hole. Black hole is a space-time region that has a strong gravity that nothing can escape. So the point of no return is called the event horizon. And now, today, we know that black hole actually exists. In 2002, Genzo found the first indication that black hole may exist. They found there exists a supermassive black hole at the center of our Milky Way, and this is a reference. And in 2015, the NIGO collaboration first detected the gravitational waves of the merger of two black holes. And more recently, 4 years ago, the Event Horizon Telescope collaboration took the first ever image of the black hole, which lies at the center of the galaxy. And this is a picture of the black hole. So today we know that the black holes actually exist. So this is a very brief introduction on black holes. And then we will talk more about the black hole thermodynamics. So the next part is from black hole thermodynamics to the black hole chemistry. And the next few slides are based on this paper, Black Hole Chemistry, Thermodynamics with Lambda. So what is black hole thermodynamics? In 1970s, Beijing, Carter, and Hawking proposed the 4 laws of black hole thermodynamics. The zeroth law is that the surface gravity kappa is constant over the event horizon of a stationary black hole. And the surface gravity kappa here will be interpreted as Hawking temperature later. And the first law is for a general black hole that has a mass m, an angular momentum j, and a charge q, we have the differences of the mass between solutions. The delta m is related to the differences between the area of the event horizon, delta a, and also delta j and delta q, where j is the angular momentum and the q is the charge. Omega is angular velocity and phi is the electric potential. So this can be written as delta m equals T delta S plus some work terms. And T is the temperature, S is the entropy. And the second law of the black hole thermodynamics is the Hawking's area theory, which means that the area of a black hole event horizon can never decrease. So we have delta A is greater or equals to 0. And the third law of the black hole thermodynamics is that it is impossible for us to reduce the surface gravity kappa to 0 in a finite number of steps. So as we can see, the four laws of the black hole thermodynamics is very similar to the four laws of thermodynamics that we learned in high school. So next, how can we from black hole thermodynamics to black hole chemistry? In the previous slide, we know that we can write the first law of black hole thermodynamics as delta E equals to T delta S and plus some work terms. So, but in high school chemistry, we know that the pressure is also a very important variable in the chemical system. So how can we include pressure P and the thermodynamic volume V in the black hole thermodynamics? So the basic idea of the black hole chemistry is consider the black hole thermodynamics with lambda, the cosmological constant. And the main idea is to identify the mass of the black hole as enthalpy instead of energy, and the cosmological constant lambda as the pressure, and its conjugate variable, the conjugate variable of the pressure is defined as a thermodynamic volume. So in conclusion, we have this table. The left-hand side is the black hole thermodynamic quantities. We have enthalpy, temperature, entropy, pressure. And the right-hand side is the black hole mechanic quantities. We have the mass of the black hole, the surface gravity, the horizon area, and the cosmological constant. So this table means that we interpret the M as the enthalpy of the chemical system, and the surface gravity as temperature of the chemical system, and the horizon area as is proportional to the black hole entropy, and the cosmological constant is interpreted as the pressure of the system. So we have the first law. We have the first law here. So delta M equals to T delta S plus V delta P. So after this brief introduction to black hole chemistry, let's see a very simple example. The first and the most important example for the black hole phase transition, the Hawking-Page phase transition. As we know, the Schwarz ADS solution has this expression where f of r is 1 minus 2m over r plus r squared over l squared, where 2m is the horizon radius here, and L is the ADS length scale. And this is a spherically symmetric solution to the Einstein equation. And then we can compute the thermodynamic quantities, use the table in the previous slides. So we have the M of the black hole, and also the entropy of the black hole, and the temperature, the pressure, and the volume of the black hole. They are all related to the horizon radius r plus, and r plus is the largest root of the f of r here. And we can also compute the Gibbs free energy G, which is the enthalpy minus the temperature times the entropy. So it's M minus Ts. And plug in the expression of the mass and also the temperature, the entropy in the previous slides, we can compute the Gibbs free energy of the black hole system. And we can write it as a function of the horizon radius r plus. And we can also know that the r plus is related to the Hawking temperature T. So we can express the Gibbs free energy T as a function of the temperature so that we can plot the Gibbs free energy versus temperature diagram. So in this diagram, the vertical axis is the Gibbs free energy and the horizontal axis is the temperature. And as we can see, there are 3 lines. The 3 lines are the Gibbs free energy corresponds to the 3 different horizon radius. And we use the horizon radius to characterize the size of the black hole. So the large black hole has the biggest horizon radius, and the small black hole has a small horizon radius. And as we can see, if we decrease the temperature little by little, and after this THP called the Hawking page temperature, the original preferred state is the large black hole, but after this Hawking page temperature, the Gibbs free energy of the radiation becomes lower. So the preferred state is a radiation state. So this means that after this Hawking page temperature, our black hole system becomes the radiation. So there exists a first order phase transition between the large black holes and the radiation. And for the small black hole, it always has a very high Gibbs free energy, so it is not a stable state. So this is the basic idea of the Hawking page transition. And also, we can compute the coexistence line of the large black hole radiation if we find the pressure versus temperature phase diagram. And in the pressure versus temperature phase diagram, we can plot the coexistence line. So the P, the pressure, is a quadratic function of the temperature, and it has no terminate, has no end point. So it is very similar to what we know in the solid liquid phase transition. So we can kind of make an analogy that large black hole is liquid and the radiation is solid phase. So this is just an analogy between the chemical system and the black hole system. And then after talking the black hole phase transition, there are more chemical phenomena in the black hole system. The most famous one is the black hole triple point. Just like water, in chemistry, we have water. It has the liquid, the solid, and also the gas phase. And we have the triple points of water, where the 3 phases meet together. And for black hole, we also have the triple point. The triple point is defined as a point where the 3 phases coexist. And there are many papers studying the black hole triple points. And in these 3 papers, the multi-spinning higher dimensional black holes and also the black holes with higher curvature corrections, they can all have the black hole triple points. And these are the references for these studies. So back to our topic today, can we go beyond the black hole triple point? So we want to study the black hole quadruple point or quintuple points. So these are more complicated ones. And the black hole quadruple points was first found in this paper. So let's talk about the setup of the system. We consider the 4-dimensional Einstein gravity coupling nonlinear electron dynamics. And the action of our theory is like this, where G is a determinant of the metric tensor, and R is a Ricci scalar, lambda is a cosmological constant, and alpha i's are some coupling constants, and the F squared is F mu. F mu is the electron magnetic field tensor. So as we can see, if we just have alpha 1, it can be reduced to the Einstein-Maxwell case. And so here we have the higher order terms of this field tensor F. So by varying the action, we can get the Einstein-Maxwell equations. It is a generalized Einstein-Maxwell equations, where the G mu is the Einstein tensor and the LEM is the Lagrangian for this electromagnetic part. So if we have the field equations, how do we solve it? We can assume some metric ansatz and then some series of the coefficients U. So we make an ansatz that is the spherically symmetric static black holes. So we have minus U dt squared plus 1 over U dr squared plus the spherically symmetric part. And A is the for potential in this case. So after making this metric ansatz, we can get the simplified field equations here. And if we make the power series of the phi and the U here, we can find the coefficients in front of the R. We can find the BIs and also the CIs by solving this field equation here. So we get C1 is minus 2m. It is a random radius. And also we have Ci, which is in terms of the Bi minus 1 here. And the Q is the integration constant. It is a charge. And we also have the B5, B9, and so on. So we get the coefficients in these field equations here. So let's consider a simple case. We focus on a setting in which the R0 and the independent for I is equal than 7. So we have the solution here. Phi has this expression and U has this expression. So, and we can also check that if we have only alpha 1, so alpha I are said to be 0. If I is greater than 1, we can recover the Einstein-Maxwell case, which means that the electric potential is Q minus R, Q over R, and the U is just very like the charged black hole, but with this ADS length scale term. So after get the black hole solution, we can compute the thermodynamic quantities of the black hole solutions. So we have entropy here. S is proportional to the area of the event horizon. So we have the entropy is equal to pi times the R plus squared, where R plus is the horizon radius. And we can also get the pressure. The pressure is related to the cosmological constant. And for the ADS case, it is related to the ADS length scale L. P is equal to the 3 over 8 pi L squared. And we can also compute the volume by computing the variable of the thermodynamic. So we have the volume is equal to 4 pi times R cubed over 3. And also we can find we can compute it by avoid the cortical singularity. So we have here. And also we can find the equation of state. The pressure, there is a formula that related the pressure and the temperature. So it is very like the equation of state, in the chemical system, like PV equals nRT. So this is an analogy of that. So this is the equation of state for black hole. So now let's talk about the quadruple points in black hole phase transitions. After getting that the thermodynamic quantities we've seen before, we can compute the Gibbs free energy by mass of the black hole minus the temperature times the entropy of the black hole. And we can also plot the Gibbs free energy versus temperature diagram, just like before. And as we in this diagram, there are four phases, the four blue line, and the stable phases, the three red line here. And we can also see that if we just lower the temperature from here, if we lower the temperature, originally the preferred state is the largest black hole, because the largest black hole has the lowest Gibbs free energy. But when we decrease the temperature at this point, there is a first order phase transition from the largest black hole to large black hole to the small black hole. So, and also at this point, we can observe the phase transition from the small black hole to the smallest black hole. So, in the Gibbs free energy diagram, we can easily see the black hole phase transition. So what are the quadruple points? Can we say in the diagram? So let's look at the feature of the diagram. There are three swallowtails, and there are four phases. But if I change the parameter, the temperature of the system, the locations of these three swallowtails will change, and we can make the 3 points meet. So this is a diagram. And if we choose this parameter, specific pressure, and also the charge here, coefficients here, if we choose these specific parameters, we can make the 3 points. So the three swallowtails meet together, so we get these points. It is the intersection of all the 4 phases. So as we can see, in this Gibbs free energy diagram with this specific parameters, we can find that if we just focus on a specific temperature, for example, a temperature here, as we can see, one temperature can correspond, one temperature can correspond to 4 blue lines. So this means that at this specific temperature, the 4 phase blue lines can coexist. So this is called a quadruple point. So the intersection here, the intersection of these blue lines is called the quadruple point. So the quadruple point is where the 4 phases meet together, where the 4 phases connect. And also we can use the temperature and radius diagram to better understanding the quadruple. So at hand side, in this diagram, as we can see, if we have from this temperature range from here to here, we can find the 4 phases coexist. And in this, we can also see that if we have one temperature, it can correspond to different horizon radius. So this means that at one temperature, we can find different sizes of black holes. So this one. So this means that for these quadruple points, we have 3 swallowtails, and we have 3 pairs of local extremal in this diagram. And also, we can also find quintuple points and also higher order points. So for generally n-tuple critical points can correspond to n-1 swallowtails in this diagram, corresponds to n- local extremo in this diagram. And from now on, let's talk about the quadruple points in the black hole phase transitions. We have the off-shell here. In the previous slides, and the on-shell Gibbs free energy. Let's talk about the off-shell Gibbs free energy. Off-shell Gibbs free energy means that here, it is to be the Hawking temperature. It is just some ensemble temperature that's before. So it is some constants that we set. So free energy is equal to the m minus TES, where TE is the ensemble temperature. So expression of the Gibbs or the offshore Gibbs free energy here. And also the TE is our input. So numerically, we can input some value TE here to plot the Gibbs free energy diagram. And in this offshore Gibbs free energy diagram, it is the offshore Gibbs free energy versus the horizon radius R plus. And if we choose some ensemble temperature, for example, the ensemble temperature here, we can find that there are 4 local minimum RSS, RS, RL, and also RLL. The RSS is the smallest black hole, and the RS is a small black hole. RL is a large black hole, and RL is the largest black hole. And there are also 3 local maximum. And the local maximum in the offshore Gibbs free energy diagram means that there are 3 unstable phases. And the 4 local minimum here is the 4 stable, and all the other points on this curve are some transition states. For the stable phases, we have the RSS, RL, and the RLL. Now we can also say that in this specific ensemble temperature, the 4 share the same free energy. So this is the structure of the off-shell Gibbs free energy diagram. And now let's talk about the off-shell Gibbs free energy at some different ensemble temperatures. So the black one is the intermediate temperature, as we seen before. And if I lower the temperature, if I lower the ensemble temperature, it becomes the blue curve. And if I raise the ensemble temperature, it becomes the red curve. So as we can see, only in this ensemble temperature, the 4 stable phases share the same Gibbs free energy value. But if we just lower the Gibbs free energy, if I just lower the ensemble temperature, the smallest black hole has the lowest Gibbs free energy, and the largest black hole has the highest Gibbs free energy. And also, if I raise the ensemble temperature, as we can see, the smallest black hole has the highest Gibbs free energy, and hole has the smallest Gibbs free energy. Here, for the red one, the black hole phase are described by the Smoluchowski and the Smoluchowski equation, diffusion equation, certain potential, and the Gibbs free energy G here act as a potential in this diffusion process, and the rho of TR here is the probability that the black hole system will stay in the size that has the black hole radius R at time t. And the D here is the diffusion coefficient. And the beta is the inverse temperature. So by solving the Smoluchowski equation, we can solve it for the the time evolution of the probability distribution though. And to solve this equation numerically, first we need to set some initial conditions and also boundary conditions. For the initial conditions, we assume that our initial state to be picked at one of the four stable phases. Like for example, it can be the RSS or RS or RL or RLL. So we assume that our initial state is to be picked at a stable phases, and it's a Gaussian wave pocket. So the initial state to be some Gaussian wave pocket and has the expression here. This is the Gaussian wave pocket. And also for the boundary conditions work in the ADS, the asymptotic ADS case. And in the Gibbs free energy diagram, as we can see, if the horizon radius is lower enough or higher enough, the Gibbs free energy will become infinity. So it is reasonable to set the reflective boundary conditions at the left-hand side and the right-hand side. So we set the boundary, the reflective boundary conditions at the two ends. So this is our reflective boundary conditions, which means that the current vanishes. So after solving the Smoluchowski and also set the initial boundary conditions, we can find the time evolution of the probability distribution, though at some temperature. So here, first, I worked on at the intermediate temperature, this case, the black curve. So the first one that I assume the initial state is, so initially it is pocket at the largest horizon radius. And as we can see, as time goes by, the probability of this largest black hole phase will decreases. So the peak decreases as time goes by. And also, if we focus on the other three horizon radius, the other three stable phases, the largest black hole, the small black hole, and the smallest black hole. As we can see, the probability of the largest black hole leak to the other three states. So the probability of the other three states will gradually increase, and also increase here. So this means that the probability of the initial state can link to the other three stable phases. And as we can see, after a sufficiently long time, like the time here, black hole will decreases to the other three states, to the largest black hole and the small black hole and also the smallest black hole. After sufficiently long time, this probability distribution will be, and for the four stable phases, they all share the same probability. And also for the initial small black hole and the initial smallest black hole. So for the initial small black hole, it is picked at the small black hole initially, but it will also leak probability to the other three states. And we can also see a little peak for the smallest black hole. This is because the small black hole and the smallest black hole are very close to each other. So we could say a little peak for the smallest black hole here. And also, the initial state is the smallest black hole case. There is a little peak in the small black hole. And now let's focus on a two-dimensional diagram other than the three-dimensional one. We just focus on the probability physics. So we get the four curves here. The purple one is the largest black hole, and the orange one, the red one is a small black hole and the smallest black hole. So this is just the two-dimensional versions time evolution of the probability. As we can see, no matter of the initial state, the four cases, after a sufficiently long time here, they all share the four phases, all share the identical phylostationary probability. This means that at the quadruple point, we have the four phases coexist together. And so finally, the space-time is a superposition of the four stable phases. And then let's talk about the first passage events. For the first passage events, first let's talk about the definition of the first passage time. Time for a given initial state is defined as the required time to first to the top of the nearby of the free energy barrier to the unstable phases. So in this diagram, for example, the first passage time given initial large. So after some calculation of first passage time distribution for any given initial phase, so we have the four first passage time for the four initial states. And also we can plot the first passage time distribution as the function of the time. So this is the first passage time distribution diagram in this intermediate temperature. So at this temperature, as we can see, in all the diagrams, there is a peak for these curves. And the local peak means that at this time, it will have the highest probability to finish the first passage event. So we can use the location of the peak, the characteristic time here, to mean the first passage event. So as we can see, for these four diagrams, this one is the initial largest black hole, and this is the initial small black hole, and this is the hole. So from the first passage time to the smallest black hole first passage time, as we can see, the characteristic time become lower and lower. So the time here is very, very large, and the time for the large black hole is smaller than this. And also for the initial small black hole, the time here is lower than this two. And also this is the smallest one. So this means that it is it is easier to finish the first passage event for the smallest black hole, and for the initial largest black hole, it will need more time to across this maximum. So this means that the first passage time can capture of the Gibbs free energy barrier here. So this is the first passage time distribution for different ensemble temperatures. Originally, we have this diagram for different, and we can also find how the first passage time is related to a different ensemble temperature. Let's take the largest black hole, for example. For the largest black hole as the initial state, so our initial state is here or here or here for different temperatures. So at figure A, has the smallest temperature, and the figure B has the intermediate temperature, and the figure C has the highest temperature. So as we can see, as temperature increases from A to C, the peak time becomes larger and larger. So this means that for the highest temperature case, the first passage time for the largest black hole is the highest one. This means that for the largest black hole at high temperature, it is harder to cross this barrier, and for the low one, hole is on there. So the first passage distribution. So this means low temperature for the shorter time here, and in long time, as we can see, the four stable phases are all reach a stationary case. So it becomes stationary, but it is different from the intermediate temperature one. The four stable phases have different probability distribution. So the blue one, the smallest black hole, has the highest probability, and the largest one, the purple curve, has the lowest probability. The most stable black hole. So it is with the offshore Gibbs free energy. So the smallest black, lowest Gibbs free energy. So that's why the probability of the smallest black hole is the highest. And also for the initial large black hole, the orange probability will decreases, and the other three phase increases. First black hole is the first of here, as we can see, is the same as this one, and they are all determined by the structure of the Gibbs free energy here. And also for the small black hole and the smallest black hole, we observe the similar situation. For the small black hole, it will decreases, and because the smallest black hole and the small black hole are very close to each other, so the will have a peak here. So it is the same case here, and also have after they will reach stationary, which is just structure of the energy here. See solution for stable high temperature is the option for the high the most stable physics is the and the Gibbs free energy. State is not here, so it will state there are very states. But for the initial large pole, the orange one, as we can see, finally, the purple one, the largest black hole will, and the other three are the probability for the other three phases are very small. And also for the small black hole and the smallest black hole, finally, the purple one, the largest black hole, will dominate. So now let's make a conclusion. So initially, the probabilities will lead to the other three states. This means that the black hole phase transition process can indeed happen. And the early time behaviors depends on the first passage time. And finally, the probability distribution will become stationary. And we have the the probability for the fourth, and the probability for the four stable phases is just the structure of the Gibbs free energy. And this is differences. You can learn more about the black hole phase transition, this, and also Yang, Shaowang, Yu Xiaoliu, Wang Yongqiang, and Lia Abshori for helpful. Thank you for your attention. If you have any questions, please free to ask.是在腾讯会议吗？我好像没看见，不好意思，是在。嗯，我看到了，不好意思，不好意思。第一个问题是大黑洞向小黑洞的相变，在现实中可以观测到吗？就是现实中我们可以观测到某个黑洞世界突然变小。对于为止好 像还没有证据可以观测到这个微动相变的非常新。我们 black hole phase transition 可以研究大小的转这个triple point or the quadruple point 可以认为是black hole superposition 是这样的一个物理图像。
Same question, the Chinese. Is it
Sorry.
sorry of the phase transition?
Could you repeat?
I guess it's the same for this kind of phase transition in our universe.
The very hard to answer because I didn't say any for this transition.
It's possible to happen in the real universe, this kind of phase transition.
Right.
Okay. Thanks.
reproduce the RT formula without knowing the RT surface in advance. This is the strategy. Okay. If you calculate the entanglement entropy of A, which equals to entanglement of B, where A and B forms a pure state, you should do a summation of all the P threads, which between A1, AI and AJ, between BI and BJ, and those intersecting P threads between AI and BJ, and with the corresponding weight. The weight is given by some arbitrary homologous surface that anchored on the boundary of A. You should consider all the configuration of homologous surface. After the surface was given, we can read all the weights, which are the number of times the thread intersect with the homologous surface, and minimize the summation, which means that you should find the homologous surface which gives you a minimal summation of these terms in the bracket. Okay, this is the strategy which we can get rid of the information from the RT formula. Before we enter an explicit example, we give some general properties the weights should satisfy. For example, this threads, the weight for the threads that comes from some subset inside A to some subset inside B, this thread should be the weight of such kind of threads should be odd numbers. For example, 1, 3, and 5, because they just switch from one side of the homologous surface to the other side. But the weight of the P threads between this AI AJ or BI BJ, they should be 0 or even numbers, because the endpoints are in the same side of a homologous surface. It should pass through the homologous surface for even numbers. Let's go back to the two interval case. For the two interval case, you have two possibilities. To minimize this summation, you should choose the homologous surface that gives you as small weight numbers as possible. Now you can consider those weights for AI and BJ, which should always be odd numbers, and the minimum value is 1. So you take them to be 1. And the A1, A2, B1, B2 threads, their minimum number is 0. Actually, but you cannot find the homologous surface that gives you this omega A1, A2, and omega B1, B2 to be 0 simultaneously. Actually, the only one of them can be 0. So you have these two possible choices. Actually, these two different choices are exactly this connected phase and disconnected phase, which gives you the entanglement entropy this way. And according to our definition, that we should minimize the summation, so you should choose the one that gives you a smaller entanglement entropy, which is exactly the phase transition of the RT surface. Okay, now we can give a summary to our talk. Actually, our PE thread configuration gives a reformulation of the RT formula in ADS3 CFD2. We want to go further for higher dimensional cases, but as we said that for non-spherical regions, the PE flow actually, a naive calculation of the PE flow does not reproduce the RT formula. This is because that for non-spherical regions, you always get some flows that was ended on the same side of the RT surface that passes through the RT surface, which means that we should also consider such kind of PE threads contribution. This is a plausible, a reasonable guess for the solution, but we are still working on this. So it's quite hopefully that this will solve our problem for non-spherical regions and give a reformulation of the RT formula in generic space-time for generic shape. And actually, a more interesting future direction is that how to describe the space-time with those PE threads. Actually, we can take the ideal space-time as some space that's full of the PE threads in a similar way as the B threads. So this is an interesting future direction. And how does the PE threads connected to the other description of space-time, other toy models like the tensor network? Actually, the calculation of the entanglement entropy using the PE threads is exactly the same as the one we calculated the entanglement entropy in the tensor networks. The entanglement entropy equals to the number of times that threads the path in the tensor network that cut the tensor network. You should count the number of the paths, and the number of counts will give you the entanglement entropy, which is quite similar with our description with the PE threads. Actually, the PE threads has a quite well-defined continuum limit, unlike those tensor networks. So, in some sense, the PE threads gives you some well-defined continuum limit of tensor network description for the ADS safety. Okay. Thanks. My talk finished here. If you have any question for, please ask me directly. Okay, is the host here?
Sorry, can I ask a question?
Oh, okay.
Okay. By reformation for space-time, are you talking about describing more general space-time using this kind of bit threads method, right?
Oh, right.
I see. Is there any known example of reformation of space-time aside of ADS space-time?
Even in ADS spacetime, the reformation of spacetime is not very successful. For example, you can use tensor network, the mirror tensor network, and you can read from the tensor network for the metric of spacetime, which is quite close to the ADS metric. But this tensor network does not have a well-defined continuum limit. People give proposals to give a continuous limit of the mirror tensor network, but those are not quite convincing, and may have its own problems. Also, the tensor network is not some exact description of the entanglement structure. It's some actually this is a simulation that is not exact. So it has some problems. Also, the B-threads reformulation of spacetime need the metric of background spacetime in advance to determine the B-threads. It's said that the spacetime is full of B-threads which has a finite size. It's some cylinder in spacetime with radius with its cross-section area to be 1/4G, something like that. But actually, they have all their own flaws. Even in our case, in the PE threads, so far we depend on the background, the metric of spacetime in advance, and we hope to go further beyond that. For example, whether we can read the metric based on the PE thread picture without knowing the background metric in advance.
I see, thanks.
I also have a question. So if before taking continuum limit, this theory should be due to some kind of finite end theory.
Due to what?
So you said there is no well-defined continuum limit.
For tensor network, I guess, yeah, I guess there's no well-defined continuum limit.
Then this means that the dual system, I mean, the CFT side has a finite number of degrees of freedom. So
Yeah,
this
if you
means that,
if you use tensor network to describe the entanglement structure, and it's made for describe the entanglement structure for those discrete systems.
yes, then this means that the bulk theory has a vanishing Newton constant, like finite Newton constant. I mean,
Yeah, I guess right.
so can you see some kind of correction to area law from this point of view? So usually,
this can there are toy models based on tensor networks. You can give some bulk degrees of freedom on the bulk tensor network, which gives you some quantum correction to the RT formula. Yeah, that is the way you get corrections.
Okay. Oh, I see. Thanks. Any other question or comment? Yeah, if not, let's thank the speaker. Thank you.
Okay, thank you.
And let's close the session and let's thank all the speakers of this session. Thank you very much.
Okay, thank you. Good.